state tables, state diagrams, and moving between them. When we think about programming and doing things repeatedly, for instance, when we execute instructions in a while loop or a for loop, we wish to hold data from one iteration of the loop to the next. To implement this in hardware, we need to think about how to hold the data from one state to the next. And the way to do that is by using sequential circuits. One sequential circuit that we've been using is the flip-flop here. And the structure of a state machine that we can design in digital logic is composed of a block that is purely combinational, or combo, and a sequential block, which we can call just a register. Now, the combinational block has some number of outputs that go to the register. We'll call this n. And the register output wraps back around to the combinational logic input. If we have n bits coming in, then we are going to have the same number of bits coming out here, n bits, because it is an n-bit register. For the combinational block, we will also have a generalized set of inputs. We could say we have k bits of input, and we also have some number of bits of output. We'll call it m. M bits output. So there are no limitations on the number of bits for k, m, and n. No limitations. The whole idea behind drawing the sequential circuit like this is because it decomposes problem into combinational logic and the register. A register can be implemented as an array of flip-flops. And the combinational logic this can be implemented using Boolean algebra, or truth tables, or Karnaugh maps, K-maps, list here. Another one that we're going to introduce in this discussion is state diagrams. So let's consider a sample state diagram. A simple sequential circuit. So an example. Up, down counter. with a 4 count. So 4 count, which means it counts 0, 1, 2, 3, like so. Let's draw an example circuit here, or an example state diagram. We'll start at the number 0, 0, 0, and then it goes, when counting up, to state 1. So the transition is from state 0 to state 1. There's an input. Let's say it counts up. I equals 1. Count up. I equals 0. Count down. So we have an input 1 for counting up. What is our output? Well, let us take the trivial case where the current state is equivalent to, where the output is equal to the current state. So we will just say the current state is 0, 0, 0. So we will say the output is 0, 0. Let us list state number 2 now. 1, 0. It counts from 1 to 2 when we have input 1, and our output when our current state is 0, 1 is trivial output 0, 1. Our third state, 3. When we are on count 2, we have an input of 1, we count up. We go from 2 to 3, and our output is still this trivial state value, 1, 0. And when we are in state 3 now, and we have an input of 1, we wrap around to 0, 0, 1, and our output is the trivial value for the current state, 1, 1. What about if we wish to count down now? Well, we need to take an input of 0 instead of 1. So if we are in, say, state 3 and we wish to count down, we will go to state 2. Our input value is 0, and our output is the trivial value for the current state. So 1, 1. It's the same. From 2, counting down, we go to 1. Input is 0. Output is 2. From 1 to 0, the input is 0 because we are counting down. And the output is 0, 1. And from 0, we're counting down. That means we wrap around to 3. Input is 0. And our output is, let's make this a little tighter. Our input is 0, and our output is 0, 0. Now, if we look at an arrow that connects one state, or state 0, and another state, state 1, we see an edge, this arrow, which has some labels. We have above the slash a 1, this is the input, and below the slash we have 0, 0, this is the output. So for a state machine, we have several components. Set of states. So this is our set of states are these circled portions here. And we have a set of edges. Each edge is an arrow, which shows a transition from one state to another. So an edge is a transition from one state to another. Has input and output. Running out of space here. Let's give ourselves a little more. Well, let's go back to our combinational and let's go back to our sequential circuit block diagram. This is our combo logic, and this is our register, which is purely sequential. We have our current state, is the output from the register. Next state is the n-bit output from the combinational logic. The input, K input, is the input to the state machine for an edge. And here we have the m-bit output. Of an edge. So in this state machine, we can say, well, let's label our variables here, k, m, and n for n bits. So n bits of state, m bits for output, k is for the number of bits of input. We have k equal to 1, m equal to 2, and n equal to 2. Notice that we have 4 states, 0, 1, 2, 3, and 2 bits. If we have s states, then n is equal to log base 2 of s, where you have s number of states. If s is not a power of 2, things get a little bit interesting. So if s is equal to 5, log base 2 of s is slightly greater than 2. But 2 to the power of 2 is 4, so we need to have 1 extra bit for 5 states. So we need to take the ceiling operation. This means round up always. Round up. Okay? So we have a 2-bit up-down counter. A 2-bit up-down counter. Let's try redrawing it here. And look, we have a block that's combinational logic, and we have a register. How do we build the register? A 2-bit register is very straightforward. Let's draw the 2-bit register now. We can have one D flip-flop, a clock, Q, Q prime, R, and P preset, and then we have a second flip-flop. We have D, clock, reset, preset or set, and Q prime. The clocks are all connected together. The reset signals are all connected together. And then the preset, these are just connected to logic 1. And now we have 2 bits of output. Notice we also get the inverted values for free. Array of 2 flip-flops implies 2-bit register. What about this other part, the combinational logic? The register was the easy part, but the combinational logic may be a little bit harder until we remember that combinational logic can be implemented as a truth table. So let's redraw our state machine diagram for the up-down counter. 0, 1. Let's give ourselves a little more space. And when we count up, let's draw the count up circle. It just goes in a circle. It's input 1, output is current state, so 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Remember, we're just saying that the source state bits are copied to the output bits. Makes it really trivial. Going in the opposite direction, we have input 0, current state is 0, 0, so we output 0, 0. 0, output this value here, so 1, 1. Going backwards, input is 0. Current state is 1, 0, so 1, 0. And, whoops, input is 0, current state is 0, 1, so the output will be 0, 1 for this condition. Truth table. How do we implement this state diagram as a truth table? Well, a better question, how do we represent this state diagram as a truth table? Well, we have input I, right? So copying from before, k equals 1, m equals 2, n equals 2. Input I, we have A for the higher order bit. We'll call this bit for the higher order bit A, and then B for our lower order bit. So Now we need to think, well, we have m equals 2 for our output bits. So O1, O2, and then n equals 2 for our state bits. For our next state bits, so we need to have, well, we already have a for these variables here, but what about these variables? They should be related to a and b, but marked as a next state. So we will call them a plus and b plus. Let us draw out the truth table. What is interesting here is the output O1 and O2 are just copied values from A and B, respectively. So we're going to use that to our advantage in just a moment. But before we do that, I want to go through this step by step so you see how to represent the edges in the truth table. Each edge in the state machine represents a row in the truth table. How many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8. This is a complete state machine diagram, and therefore we can fill in all the details for each row in the truth table. Let us look at this edge first. Unclutter it here. Going from state 0, 0, our input is 1. We are looking at 1, input 1, and input state 0, 0. The outputs are 0, 0, and the next state, the output is 0, 0, and then the next state is 0, 1. Let's back up just a little bit here. So 0, 0, I want to call attention for the current state for 0, 0, and then input 1 for input 1. Now the output is 0, 0, 0, 0, and 0, 0, and our next state 0, 1 is 0, 1. So we have handled one row now. Next, let's look at this edge here. So the current state is 0, 1, and the input is 0. Input is 0, current state is 0, 1. We are here. Output is 0, 1, and the next state is 0, 0. Output is 0, 1, the next state is 0, 0. Let us look at 1, 0 now. Let us look at the 0, 1 to 1, 0 transition. Okay, so we have a current state of 0, 1 and an input of 1. Input of 1 and a current state of 1. That is this row here. Working on this row here, output is 0, 1. So output is 0, 1. And our next state is 1, 0. 1, 0. Looking at this transition, bit interesting. We go from state, we have input 0, and we transition from state 1, 0. So 0, 1, 0. Zero, 1, 0, we are now on this state here. We are now on this state here. So our output is 1, 0, and our next state is 0, 1. Our output is 1, 0, and our next state is 0, 1. Notice a pattern here. The current state, 0, 1, is copied to the output. The current state is copied to the output. This is a condition that I used as a shorthand to make implementation of the output bits incredibly easy. Because of this, we can trivially fill in O1 and O2. We just copy over this to here, and then we can copy like so, and like so, and then here, and we're done with the O1 and O2 columns. We just need to worry about the current state, input, and the next state now. And we can ignore the output bits. This is one nice property of counters, but it's not something that you can apply across all state machines. It's just a trick that we used here. So next, if we are in this row here, say we wish to fill this in, well, we have an input of 0 and a state of 0, 0. So here, and an input of 0. Our next state is 1, 1. 1, 1. Say now we're done here and we wish to look at this transition. Our current state is 1, 1 and our input is 0. So the next state is 1, 0. 1, 0. On this row, we have an input of 1, and we are in an input of 1, and we are in state 2. So what is our next state? It is 3. And then finally, if we are in state 1, 1, and we have an input of 1, our next state is 0, 0. And now we have a completed table for the combinational logic which is listed here by the star. We've already shown how to implement the 2-bit register. This is very straightforward. So we can just copy that, and now let's optimize nominally our truth table with K-maps. O1 is equal to A, and O2 is equal to B trivially. We don't need to use K-maps for that. What about A plus and B plus though? A plus, you have input I and state AB. We are looking at this column, right? Going right down from top to bottom. 1, 0, 0, 1, 0, 1, 1, 0. Then we have B plus here. I, A, and B. And now we're going to look at this column instead. The B plus column going from top to bottom. 1, 0, 1, 0, 1, 0, 1, 0. So we can group B plus very quickly. B plus is equal to B prime. What about A plus? A plus is a little more difficult. Well, we have 1, 2, 3, 4 singleton groups. This is pretty ornery. So we have A plus equals I prime, A prime, B prime, or actually let's draw this a little bit in a different location so we can actually work with it using Boolean algebra to simplify. So A plus equals I prime, A prime, B prime, or I prime, AB, or I, A prime B, or I, A, B prime. So this is kind of interesting. We can factor out an I prime from two of the terms and an I from two of the other terms. So I prime, A prime, B prime, or AB. And then we can OR this with I, and it with A prime B or AB prime. This is equal to I prime A XOR B quantity prime, or I A XOR B. So we're using Boolean algebra to simplify A plus. So let W equal A XOR B. This will help us to visualize a little better. A plus equals I prime W prime, or I W. So A plus equals I XOR W quantity prime, or I XOR W, which is equivalent to I XNOR, or XORed with A XOR B. We can now draw the sequential circuit. Let's copy the registers first. So we have, well, let's copy the flip-flops first. So we have our first flip-flop, D, Q, Q prime, our clock, reset, and our preset signal. We also have a second flip-flop, D clock, Q, Q prime, reset, preset. Let's bring our signals back around. So this is going to be a little bit messy here, I apologize. Try to keep it as neat as possible. So here we have A prime, B, B prime. We also have an input variable, I. In our equations for A plus and also B plus, notice that we don't have an inversion of I. If we did need an inversion of I, we would use an inverter. Since it's not required, we will leave it out here. So our trivial input is B plus, or which is just equal to B prime. And then our A plus value is just A XOR B, like so. And then we have that output to an XNOR gate that is combined with input I. Our outputs come from A and B respectively. O1 from A and O2 from B. And then we need to connect our clock, reset, and preset signals. So first, let's do the clock signal. And then label that OK, CLK. And then we can reset to state 0. We don't necessarily have to start in state 0. We can reset to a different state if we wanted to. But for the purposes of this video, we're just going to start in state 0, which means we can connect both of the R signals from both flip-flops to the reset signal. And we don't use presets, so we will connect them both to a logic 1, or VDD. And here we have the final implementation of our up-down counter. Let's try implementing this in a simulator. I use LogicWorks, but you can use your favorite simulator. So first let's place some flip-flops, which I will take from simulation logic. We'll use a D flip-flop to implement the 2 bits of our register. And now let's bring the signals around. Here's B prime, and then B. Oops, we want B from here. And then A prime, and A, right? And then we need I. Let's label our variables. I, A prime, B, oops, let's try that again. B and B prime. Now, remember that we are not using an inverter for I because the inverted I signal is not needed in the circuit implementation that we have. Let's review. We have only 2 logic gates required. So let's use this to our advantage. We don't need an extra inverter for I, otherwise we would. So we need our logic. Let's go to simulation gates. We need first an XOR 2. Let's place it here. And then we will take an XNOR 2. Place it here. So we have A XORed with B, XNORed with I. If memory serves correctly, A XORed with B and XNORed with I. And that checks out with this equation right here for A plus. And then we just connect this input for the lower order bit to B. We need our clock signal here. Connect the clock signal to both clock inputs on each register. And then we need to reset to state 0. So connect the reset signal to the reset pin of both flip-flops. And then we don't need this set pin for either of these flip-flops, so what we're going to do is tie it to a logic 1. In LogicWorks we're going to go to connectors, the plus 5 volt symbol, and then just connect it at the top of each of these D flip-flops. And now we are ready to place our simulation IOs, our binary probes, and our binary switches. So we need one for clock, we need one for reset, and we need one for I. Output 1 and output 2 for A and B respectively. Let's put a name here, O1 and O2. So let's try simulating this circuit and see how it works. We are in the reset position right now because the reset signal is active low and this binary switch is set to 0. So no matter how we clock it, we're always going to see an output of 0, 0 here on our output probes. And if we set it to 1, we are now in the state machine mode. We're now in regular mode. We can run the state machine without having to reset the system. Let's try clocking. Every time we see a 0 to 1, we should see this count 0, 1, 2, 3. If our input I, let's set it to 1 to count up, we should see this count 0, 1, 2, 3 every time we clock it. It's 1. Whoops, what happened? Clock, it's clocking, but we're not seeing this count. What's the problem? We have these connected appropriately. We have A XORed with B, XNORed with I, right? And then let's check to verify. A XORed with B, XNORed with I. Then we have B plus equal to B prime. Let's take a look at this signal. B plus is equal to, oh, here's our error. We missed that. So let's delete this wire here. And let's connect the D input appropriately to B prime. Okay, now this time it should work. So reset the system. Our input here is set to 1, so we should count up 0, 1, 2, 3. On a transition of 0 to 1, click, and we are now at 1. 1 to 0, nothing happens, but 0 to 1, we're at 2. 1 to 0, nothing. 0 to 1, we're at state 3. It's 1 to 0, nothing. 0 to 1, and a wraparound to 0, 0. So we have now verified every edge counting up on the state machine. What about counting down? Let's change the input direction with, let's change the direction with input I to 0. And now, every time we clock 0 to 1, we should see a change at 0, 0, 0, 1, or O1 and O2. So 1, 0, value 2 should go to 1. You see it transitions. Clock again, we're down to 0. We clock again and we decrement from 0, we should go to 3. And we are at 3. Decrementing from 3, we're at 2. And we have verified all the transitions going down. So we see here from the simulator how our state machine works in action. We have our combinational logic here, and we can add this wire and the wires here and here. Those act as our combinational logic, and our register is represented by these two flip-flops here. And this is how you can use a state diagram and a truth table to construct a digital state machine. Specifically, a digital state machine that counts up and down the numbers 0 through 3.